This is a hard drive. It basically has one job, and that's to remember things for you, until it doesn't. And a standard hard drive is about 2.6 centimeters thick. Now take a look at this. This device is only 2 centimeters in thickness, making it slimmer than the standard hard drive. And it's actually a fully functional NAS. Inside, it has its own computer, RAM, cooling system, and support for up to 32 terabytes of internal storage. And all of that is packed into this incredibly slim enclosure. That's pretty insane. So how did I even manage to fit everything inside something this thin? Well, that's exactly what we're gonna find out in today's video. So let's get started. To build a NAS this thin, I needed a system that was powerful yet compact. And this is what I found. Meet the ZimaBoard 2, the brain of this ultra-slim NAS. This is a tiny single-board computer. Inside the box, we got the main unit and a power brick. I also got a PCIe to NVMe adapter, SATA cables, a hard drive mounting tray, and a few other accessories. Now talking about the ZimaBoard, it's an x86 system powered by an Intel N150 processor. And that's actually a bit surprising, because we don't usually see x86 system in a such small form factor. Here we have got some nice ports on the front side, and on the back there are 2 SATA ports, and on the side there are a PCIe slot for expansion. Oh, and if you want to buy one of these, the link will be in the description. Now the ZimaBoard itself is about 3 centimeters thick, and that's already the first obstacle in building our slim NAS. If I use the board as is, the final NAS would have to be at least 3 centimeters thick, which completely defeats the purpose of this project. So I need a way to fix this. And honestly, I was also curious to see what was hiding inside this thing. Sorry ZimaBoard. After removing the top cover, there are a few more screws holding the main board in place. And don't forget to check for any hidden screws. Once everything is removed, the motherboard can finally be lifted out. This thing looks absolutely gorgeous. Now the first thing I need to do is disconnect the CMOS battery, because I really don't want any accidental short circuit, which could be a very expensive mistake. With that out of the way, now I can clean off all the thermal paste. And finally, we can get a closer look at the hardware. Here we can see the 64GB NAND, 16GB of LPDDR5 RAM, and last but not least, the shiny Intel N150 processor. And interestingly, the motherboard is actually very thin. The only components adding significant height are the Ethernet and USB ports. These things are roughly 2.5 centimeters tall, but I had an idea to fix them. You see, these ports are mounted vertically, which adds a lot of unnecessary height. Now, if I remove them from the board and remount them horizontally, the overall thickness can be reduced. As you can see, when I place them side by side, there's a significant difference in height. Now, before moving on to the next step, I'm covering the processor die with some tape to prevent any accidental damage. Now for the enclosure, I have chosen brass. I have 2 different thicknesses of brass sheet, with the thicker one being 1.5mm thick. This piece will serve as the main structure of the NAS, holding all the components in place, and it will also act as the heatsink for the CPU. Now there's one important thing to keep in mind. Is this brass sheet actually capable of dissipating enough heat from the CPU? You see, the original board was mounted to a solid aluminum block that acted as a heat sink, but in this build I am replacing that aluminum with brass, which is not quite as good as aluminum when it comes to heat dissipation. However, the brass sheet is much larger and has significantly more surface area than the original aluminum heatsink, which gives me hope that it might still perform surprisingly well, and this can be found out with a simple test. To do that, I'll use my soldering iron as a controlled heat source. I'll set it to 105 degrees Celsius and feed it roughly 18 watts of power. The goal here is to simulate conditions similar to the processor's maximum thermal limit, which is 105 degrees Celsius with a maximum power draw of around 15 watts. Before starting the test, applying some thermal paste is necessary to ensure accurate results. And to monitor everything in real time, I'm also attaching a temperature sensor. Now the heat can be turned on, and I'll run this test for about 20 minutes. After that, it seems my soldering iron is completely glitched. It can't figure out what's going on here and is showing the temperature of just 1 degree Celsius, which definitely is not true. And looking at the temperature sensor, we can see the actual temperature, which is around 62 degrees Celsius. Now after running the same test with brass, once again my soldering iron seems glitched. But the real temperature is surprisingly a little lower, which is 61.9 degrees Celsius. And all that heat is evenly distributed throughout the sheet. So without any worries, we can move forward with our build. Now first of all, we need to find the best placement for every component. Since we're working with a very small space, we need to save as much room as possible so other components like the SSD can fit inside. This placement looks best for me, and there's enough room left for the SSD. But the NVMe adapter has a small problem. It comes with a heatsink, which is not really needed here because I can directly attach the IC to the brush sheet. And it's also adding unnecessary height, so that needs to go. Perfect. With that done, the next challenge is making sure the CPU and all the ICs make proper contact with the brush sheet. The issue is that the board has several components that are actually taller than the CPU and ICs, which can block proper contact with the brush sheet. To fix this, I first mark the exact positions of the CPU and ICs on a piece of paper. This helps me figure out exactly where everything will sit on the brush sheet. Then we can cut small pieces of brass according to the shape of these components. After that, we can stack these small pieces on top of each other until we reach the required height to ensure proper contact, just like we saw in the original enclosure. Now all these pieces can be soldered in place with a gas torch and some solder wire. Once all the soldering is done, it starts looking quite messy, and the sheet itself also bent a little during this process. However, it's an easy fix by simply pressing the sheet onto a flat surface and then giving it a good blast of heat with the gas torch. After that, keep it pressed down until it cools, and the sheet is flat again. Now to give it a cleaner look, I'm removing all the excess solder with a file, and after a bit of sanding, it starts looking very neat. Now let's see if the board fits perfectly. Oh, and we already got our first obstacle. The DC input port is a little too tall and it's blocking the board from sitting perfectly flat, so that needs to go. With that done, the CPU and other ICs are now making good contact with the brush sheet. At this point, all these screw positions can be marked. Now I'm soldering some nuts onto the marked spots. After that, a bolt can be used to hold the board in place, while another nut can be used to adjust the pressure. Now the same process can be followed for the NVMe adapter, and I have added two small brackets here. This allows the adapter to be mounted just like an NVMe drive, and secured with a single bolt. And this makes it easy to remove whenever I need access to the NVMe slots. So with that done, we can now add the lid and solder it in place. I'm also adding some small nuts at each corner, which will be used to hold the cover tightly in place. And after all that soldering, it starts looking messy again. But after filing down the excess material and giving it a good sanding, it ended up looking very neat. Now it's time to make some necessary holes for all the ports. For this, after making some rough cuts, they can be fine-tuned with a file. And don't forget to make some holes for this tiny fan as well. It will help remove any hot air trapped inside and keep everything cool. Now of course, we also need some air intake holes, and I'm making them right under the main board. With that done, every single port can now be secured in place, and I'm doing this with the help of some epoxy adhesive. And finally, we can mount the main board inside. But before doing that, I'm covering all these small components around these ICs, so the brush does not accidentally make contact with them and cause any short circuit. Now the protective tape that we added earlier can be peeled off. And after applying some thermal paste, we can mount the board right into place. And carefully tighten every single nut to make sure the pressure is even on every corner. Now for the NVMe adapter, we can use the same thermal pad that came with its heatsink. And after that, the whole board can be mounted just like an NVMe drive. Now that every component is in place, it's time for the wirings. Since we detached some of the ports, we now need to reconnect them using wires. And this part needs to be done very carefully, because there's no room for mistakes. Just look at this ridiculous amount of wires, and not gonna lie, it was very exhausting. Well, enough talking. Now let's connect the DC input port. After that, we can secure the fan in place. But the fan cables are too short to reach the board now, so I had to extend them with some extra wires and connect them back to the board. And let's also connect the CMOS battery back in place. Alright, everything is looking good, but the only thing is missing now is the storage. And I already had these two drives lying on my desk, so I thought why not use them this time. Now for the SATA SSD, there's actually a lot of room left inside. I can place it here or even here. But first, let's connect everything up real quick. After installing the NVMe drive, we still have another slot left for future upgrade. And after connecting the SATA SSD, we also have another SATA slot left for expansion. So if we use 8TB drives in each slot, that adds up to 32TB of storage packed inside. Now the NVMe adapter and the main board can be connected using a PCIe extension cable. At this point, the only thing left is the power LED, which is right here. Now I'm removing this LED, and after connecting it with some wires, it can be mounted on the front panel where I already made a tiny hole for it. And with that done, it's finally time to cover everything up. As I have already soldered some nuts onto the each corner of the enclosure, so the panel can be screwed in place using some bolts. And before doing that, I am also adding a single nut to each bolt. This will lift each bolt up a little, which will also act as feet. And finally, after some sanding and polishing it up, the build is complete. Well, after all that effort, now comes the moment of truth. Will this thing even work? Well, let's power it up and see what happens. Oh, we got the light. Come on, ZimaBoard. Something's happening. Yes, finally, and it's working. So let's connect the Ethernet cable and run some tests. Now we are logged in, and here's the interface. Right here we can see the CPU load and the temperature, which is sitting at around 50 degrees Celsius, and that's actually pretty good. And over here in the storage section we can see both of our drives. Now let's drop some files and see what happens. Here I am selecting one of my footage files from this build, which is about 1.1 GB, and it immediately starts uploading. And within a few seconds, it's done. Now let's try a folder that's around 316 GB. And within just a few seconds, that's gone too. And after all that, the temperature is hovering at around 55 degrees Celsius or so, which is pretty normal for a CPU. So, while the project was a success, it definitely was not an easy one. And huge thanks to IceWhale for sending over the ZimaBoard too and making this project possible. And if you want one of these, you already know what to do. The link will be in the description. So, that's all for now, and I hope to see you next time.